Okay, this is Tom, and we're going to continue with our discussion of the Lucas-Stokey model, the 83 model. So I'm going to describe the economy and then set up the problem, and then hope that you'll dig into it with this lecture. And I'll confess, I spent many days, several times, getting inside this structure. So as simple as it is, there's some subtle things going on. Okay, so here's the setup. We're going to have a sequence of state and states, and ST, superscript ST, that's going to be the history. We're going to start at 0. So we're going to have a government that at time T has some potentially history-dependent government expenditures, and those are going to be exogenous. And then I'm going to let, following spirit of Lucas-Stokey, we're going to have representative consumer, and it's going to have a history-dependent sequence of functions for consumption, leisure, and labor that are going to be kicked out by a competitive equilibrium, and then which in turn is going to be selected by a Ramsey planner. And it's going to be a competitive equilibrium with distorted taxes. So technology is going to be simple. There's going to be this restriction. There's going to be one factor of production, which is going to be labor. Labor plus leisure of the consumer adds up to 1. There's 1 unit of town. So output's going to equal NTS. And the feasibility condition is consumption plus government expenditures are going to have to add up to labor. It's really an inequality, but I'm going to make it an equality. There's going to be a representative household that is kind of like Chapter 8, Lundquist-Sargent preferences. It's going to have the expected discounted utility, pi t of ST, that's the joint density of that history. Utility is going to depend on consumption and leisure. And the household likes consumption and likes leisure. That's important. And assume some regularity conditions on that utility function. Okay, so the way this is going to work is the technology is going to pin down a pre-tax real wage rate equal to unity for all t. So that's coming straight out of this linear technology. Okay, here's the deal. The government's going to impose a flat rate tax. It's going to be a rate on labor income at time t, history t. So this thing, there's going to be a sequence of functions it's choosing. And then there's going to be complete markets in one period era securities. And we're going to let this era security price be PT plus 1 of next period state conditioned on the history. Notice that's a superscript. So what the government's going to do is it's going to issue one period era securities every period. So then here's the government budget constraint. So government expenditures are going to equal total tax collections. Now stare at this. It's going to be a tax rate times the amount of labor that's supplied. And this tax, we're going to see, is going to distort the amount of labor that's supplied. So this NT is going to respond to this tax, but those are the total revenues. And then what's this? Well, those are the one period revenues that the government gets by selling one period era securities. That's the quantity. I'm indexing by next period state. There's our pricing kernel. And then minus, well, that's the amount I got to pay off on securities that are coming due this period. So notice the measurability assumptions about this. even though this thing is chosen, this vector is chosen at t, but it's a function of next period's state. Okay, so this thing is actually measurable with respect to st on the previous little lecture that we made. Okay, so this PT, this pricing kernel, is going to be a competitive equilibrium object. And that's that. And we're going to start with some initial government debt. It's going to be an exogenous initial condition. And this is going to play a role. So what the government's going to do, the deal is we're going to kind of do this arrow security style. The government has a sequence of these. And budget constraints, and they imply a household budget constraint. The government budget constraint and feasibility implies a household budget constraint that looks like this: consumption plus the arrow securities that I buy as a consumer from the government. That's going to be equal to my after-tax labor income plus the arrow securities that I bought last period that are coming due. Okay, so everything's on the table. So here's the objects. So there's government policy. What's the government policy? So there's an exogenous sequence of government expenditures. Now notice I made a change. I now made G a constant function of the Markov state. Okay. I made a change. This is a specialization. I'm following Lucas-Stokey. There's going to be a tax function, which in principle I'm allowing to be history dependent. And there's a sequence of government debts, which I write this way. So there's a feasible allocation. That's a consumption labor supply plan that satisfies feasibility. There's going to be a price system, which are the system of arrow security prices for all T for all histories. So the household's going to be competitive equal. It faces the price system as a price taker and takes the government policy as given. So the household chooses a consumption leisure plan, labor plan, to maximize its expected utility subject to its budget constraints. Okay. So then we're going to have a definition of a competitive equilibrium with distorting taxes. That's going to be a key thing. So the natural definition, given the price system and the government policy, the allocation is going to solve the household's problem. And given the allocation, the government policy, and the price system, the government's budget constraint is satisfied. And those statements hold for all T and all histories. So here's kind of the key thing. There's many competitive equilibrium with distorting taxes. And we can think of them as indexed by different government policies. So what the Ramsey problem here is, it's also called the optimal taxation problem. It's to choose a competitive equilibrium with distorting taxes that maximizes the expected utility of the representative consumer. Okay. Okay, this is a chapter 8 Lundquist-Sargent trick. I'm going to give an Arrow-Debreu version of the price system. And you've seen an equation like this. They're going to be useful for some things. Okay, so now I'm going to just sketch for you to get you started what the so-called primal approach to solving the Ramsey problem is. So Lucas and Stokey used this creatively, and it's been used by Chari and Kehoe, a whole bunch of other people afterwards. So here's the deal. You're going to first get the first order conditions for the household optimization problem. And then you're going to use those conditions. That's why it's called the first order approach. to eliminate taxes and prices in favor of quantities. And then you're going to pose an optimization problem for the planner that's cast solely in terms of quantities. So you're going to write down a phony planning problem that has no prices or taxes in it because they've been eliminated. So then you solve that phony planning problem for an allocation. And then after you solve it for an allocation, you go back and take the first order conditions and you back out the taxes and the prices. And that's going to be the strategy. So here's going to be the steps. And within the confines of, I know what I'm doing here is giving you, I confess, I'm just giving you a reader's guide to this quantecon lecture. Okay, so here's what you do. You go through, it's a recipe. You're going to obtain the first order condition of the households problem, and you're going to solve them for QT and taxes, the prices, as functions of the allocation. That's a key step. Then you're going to substitute those expressions for taxes and prices in terms of the allocation into the household's present value budget constraint. Now that's why present value budget constraint, why'd I do that? That's why I put those Aero de Brew prices that I got from the Aero Securities prices. That's why this step up here was done. I wasn't just doing this to show off. That's step number 2. So this intertemporal constraint that you got from this 2-step process, it involves only the allocation. It's a restriction on the allocation in addition to feasibility. And we regard it as an implementability constraint. It's an additional restriction on the competitive equilibrium allocations that comes from restricting it's additional to feasibility that comes from restricting allocations to come from a competitive equilibrium with distorting taxes. And then the next step is we're going to find the allocation that maximizes the utility of the representative consumer, subject to the feasibility constraints and the implementability condition derived in step 2. And then we're going to use the Ramsey allocation together with the formulas in step 1 to find taxes and prices. Okay. Good. Okay. So this next section is going to go through this. So here's what we do. We're going to kind of formulate the problem Aero de Brew style, which you're free to do. Households present value budgeting constraint says the present value of consumption has to equal the present value of after-tax labor income. These are these Aero de Brew prices that I've deduced, plus the initial government debt that's held by the household. That's an initial condition. Okay. So now here's what we do. We get the first order conditions for the households problem. This is the ratio of the marginal utility of leisure, the marginal utility of consumption is equal to 1 minus the tax rate. This is straight out of chapter 8 of Lundquist-Sargent. That's the Aero security price is going to be equal to this. Okay. We can rearrange that to say the Aero de Brew security price is equal to this. And now what we're going to do is we're going to substitute those in, which we're told to follow the recipe, into the household budget constraint. And we get this condition. Stare at that condition. That condition only involves, well, these probabilities. It involves the allocation, margin utility of consumption, which depends on consumption, and consumption, margin utility of leisure, which is going to depend on consumption and leisure. Margin utility consumption depends on consumption and leisure. This only involves the allocation and this initial condition. So now the Ramsey problem is going to be to choose an allocation that maximizes this thing subject to 11. And here you'll note I've substituted in feasibility here. So it's what I have to do is maximize utility of representative consumer subject to feasibility and this implementability constraint. Okay, so that problem has an interesting structure. It looks just like a phony planning problem where what we're going to do is we're going to put a single Lagrange multiplier on this implementability constraint. We're going to go from there. And this is what we get. And then we form this Lagrangian and we run with it. Okay. So now here's where I want you to take over. And we're going to get a bunch of first order conditions. And now here's the key thing. I'm just going to be a reader's guide and tell you what to watch for. You can take first order conditions better than I can, faster than I can. Okay. So when you get those first order conditions, what you'll notice is they have a different form for t greater than or equal to 1 and for t equals 0. So we have to choose, we have to maximize this thing, this Lagrangian with respect to consumption at all dates, at all histories, and with respect to labor at all dates and all histories. And when we do that, we find that the conditions break into two. There's one for time 0, which looks like this. And then there's one for time 1 and on. If you stare at them, you'll say, oh, they look just the same. Not quite. Not quite. Because here, look at this. Everything's kind of the same. Everything's the same. But look at this, what's on the second line. There's an additional term. This term here did not appear up here, and this term did not appear here. So that fact is at the heart of the time inconsistency of the Ramsey plan. And in every sense of the term, I'm just going to say that. So I'm just going to say that that's a thing to point to. So now what you can do is, so here's what the rest of this lecture is going to be. This part, we're going to roll up our sleeves and solve these things. And they have a really interesting structure. And one thing you find is that the optimal allocation depends only on the currently realized quantity of government expenditures and does not depend on the specific history that led to it. So that's a key finding of the Lucas-Stokey model. Okay, so then the rest of this is, we're going to show you a solution strategy, and the strategy is going to go like this. Freeze the multiplier, solve things, and then figure out what the multiplier is. That's what we're going to do here. Okay, so I urge you to go through that. And now, guess what? Since we're Pythonic, actually, what's beautiful about Python is it convinces you but Bob Lucas said something about this before Python was invented. He used Fortran. He said, for you really to understand a model, you got to be able to write a Fortran program or a Python program and make sure you understand the steps. So So what's going to happen is it's going to turn out that we write down these equations and stare at them, and we get, like in the finite state Markov case, we get a set of 2s plus 1 equations and 2s plus 1 unknowns, where S, big S, is the dimension of the Markov state. And so read this, there's an algorithm for solving this. And then that's kind of it. And then read this on time inconsistency. So we have various languages here that take different angles on time inconsistency. We return to our language that a continuation of a Ramsey plan is not a Ramsey plan. And what's going to play a key role is, here's this. Continuation of a Ramsey plan takes this thing as given, the margin utility of consumption times that debt, and it does not take this as given. So what's taken as given in the continuation plan, it's all about commitment. This is key right here. So you stare at that. And then we computed some stuff for a particular case. And guess what? Here's your Python program that actually computes this. So you can experiment with this if you want. And now I'm just going to wrap this up by saying that's kind of where Lucas-Stokey stopped. And now if you kind of stare at what Lucas-Stokey did, you could see that it's very tempting to formulate this as a dynamic programming squared problem. And key thing is to identify what's something that looks like a Bellman equation, and for that you can stick into the Bellman equation of the Ramsey planner. And for this problem, this thing turns out to be the key, quote unquote, forward-looking state variable. I'm just going to say that. So this thing is it's forward-looking, but it's also going to be potentially backward-looking. Okay. So now what we're going to do is we're going to copy what Professor Ken Casa did in the when he talked about the Stackelberg thing. We're going to kind of have a structure of intertemporal delegation, where we're going to have a time zero Ramsey planner followed by a sequence of continuation Ramsey planners, and those problems are going to look different. That's kind of our subproblem 1 and subproblem 2. So we're just going to do that. We're going to get 2 Bellman equations here. And that's going to kind of be it. So okay, so I'm going to urge that you look at this if you want. And it's kind of instructive to compare the sequence formulation that was above with this recursive formulation, because lots of the same economics comes through in both of them, with a slightly different formulation. First, and there's going to be something called a state. There's going to be some magic. There's going to be a state variable degeneracy, which plays a big role here. Okay. And then there's a philosophical section on the manifestations of time inconsistency, because this is a great laboratory for getting your head around what the source of the time inconsistency is in this problem. And Lucas and Stokey spent a lot of time wrestling with that. And I'm just giving you a fraction, kind of the non-controversial fraction of what they had to say about that. So you can find out about that here in this reader's guide. Then I'm going to conclude this by saying, well, here's the recursive implementation in this code. Okay, this code, I'll just say this. This code was written by somebody who is such a good programmer that he made it, in my opinion, he made it too slick. So it's deceptively short. And then what we do is some examples. An anticipated one-period war by doing these Markov chains, and then you could study what happens, and you could see how the government actually ends up manipulating prices, and what happens to government debt, and you'll see the sense in which there's tax moving. Okay, and then I want to say one final thing. It's now attempting, there's a loose end here. And this is kind of where Lucas and Stokey led it. Loose end is this. Okay, so we worked out kind of an adult version of a tax smoothing model with complete markets. And we know where Lucas and Stokey conclude is, they're very polite, but they don't get anything that look like Barrow's results of taxes follow a random walk. Indeed, tax rates and tax collections, they're an exact function of the Markov state. By the way, just as they were in our baby's version of the complete markets model. What Lucas and Stokey have added on is the government's manipulating prices. Okay, so you could ask, well, is there anything to be said for Barrow's setting? And could you do a version of Barrow, whatever that means, by sticking really close to Lucas and Stokey and have prices be still manipulated by the government? So the natural thing to do is, I'm going to link back to where I started today, is to revisit these measurability assumptions. And you could say, well, let's do exactly Lucas-Stokey, but say that the government can only issue risk-free government debt, can't issue state contingent debt, can't issue aero securities. It has to issue only risk-free. So now what's going to happen is government debt has to be measurable with respect to stuff that happened before today's Markov state, which is another way of saying that's what it means to be risk-free. Doesn't depend on what happens today. If you said you're going to pay something yesterday, you're going to pay it today. You can't say I'll pay it depending on today's state. Okay, so if we write down a model like that, that turns out to be a much tougher model to solve. People wanted to solve that model, but they couldn't figure out how. So then there's a paper by Iagari and others, 20 years after Lucas-Stokey's paper, which did that. It turns out there's another quantecon lecture, the following one after this, which is about that model. And guess what? The best way to solve that is to use dynamic programming squared. And if you do that, you pursue that, it's going to turn out that big parts of Barrow make a comeback. Turns out taxes and tax rates are no longer an exact function of the Markov state. They're history dependent. Government debt is also history dependent. So there's a lot of history dependent that comes from the incompletion of markets. By the way, just as there is in the basic Bewley model that you saw last year, the history dependence of the individual person's debt in that model would vanish if you would put in complete markets. Okay, so that's the end of my reader's guide. And I apologize that this is no more than a reader's guide. And maybe at some point you'll want to go through this lecture with a pencil and paper, or maybe even better yet with Python fired up. Okay, thank you.